Hello and welcome to Pep Talk with me, Mr. Pepperell. In this episode we're going to find out a little bit more about the radiation emitted by these things. By the end of this video you should be able to tell me a bit more about what alpha, beta and gamma radiation actually are, and you should be able to describe to me how you can separate a beam of alpha, beta and gamma radiation.
Okay, so I know we've previously talked about what alpha particles are and what beta particles are, and we've talked about the fact that gamma is just energy, but now I want to think about how we can actually determine something about the nature of these different types of radiation. And the first thing we're going to do is to use a magnetic field. So with our magnetic field, let's start with beta particles, I think, okay? So if I pass a beam of beta particles through a magnetic field, which is shown by this yellow area here, what happens is that these beta particles, rather than carrying on in their straight path that they were before they entered the field, they are easily deflected by the field, okay? And in fact, they're deflected in the same direction that we would see an electron being deflected. And from this I can conclude that if the particles deflected the same way as an electron, then it must be the case that those particles are electrons. Okay, so we know this is true. We know that a beta particle is actually a high energy electron that's been emitted by a nucleus when a neutron decays into a proton. The fact that when I aim a beam of beta particles through a magnetic field, the fact they get deflected in the same way that I know an electron will be deflected tells me that they are electrons. Now let's pass an alpha beam through the same magnetic field, and hopefully you might realise that what is going to happen is that it's going to be deflected in the opposite direction, okay? The opposite way to an electron, which should tell us it's got a positive charge, okay? Now what you might also notice as well is that the beta particle was deflected straight from its path. The alpha particle has not been deflected as much. Now this suggests to us that the alpha particle has got a greater mass, and in fact an alpha particle has got a mass that's about 8,000 times bigger than that of a beta particle. So the bigger the mass means it's much harder for it to be deflected. So from this we know it's true. We know it's got a bigger mass. We know an alpha particle is actually made up of 2 protons plus the 2 neutrons, the same as a helium nucleus. So we know it's been deflected in opposite direction to an electron, which tells us it's got the opposite charge, or in fact it's got a positive charge. And the fact that it's not been deflected as much tells us it must be much more massive, and we know that's true. Finally, we're going to pass our gamma beam through the same magnetic field, and what do we see this time? Well, we see that the gamma beam has not been deflected at all, and this tells us that the gamma radiation must be uncharged. So we've got a set of experimental results there that basically just support what we already knew about those particles. There's nothing new there. I've just shown you an experiment that proves it. Okay, but in science we don't just settle with our first experimental result, okay, because your findings need to be reproducible. And what reproducible actually means is that the same results are seen with a different experiment as well. Okay, we can do a completely different experiment and get results that show us the same thing. It also means as well that the same experiment could be done by a different scientist and he would get the same results as well. But it's very important in science that results are reproducible, that people can reproduce these results, and you're checking your results basically. So we're going to do another experiment. Okay, I'm the same scientist, but I'm going to use a different method this time, and this time I'm going to pass my beams through an electric field. So I'm going to fire my beam of radiation between these 2 charged metal plates. I've got a positive plate here and a negative plate there, negative and positive electric charges, which creates an electric field between them. And I'm going to fire my beam through that field. Now, before I tell you what's going on here, have a look at the way that my beam is splitting and the 3 directions that the path that the radiation is going to follow, okay, and see if you can make a prediction there based on what you know before I reveal to you which one's which. So just have a little look a second. Which one do you think this is going to be? Which radiation is this going to be? And which radiation is this going to be? So there we go. I've put the labels on there now. We've got the beta up here, the alpha down here, and the gamma there. So let's find out why our different particles or our different radiations behave in that way. Well, firstly, our beta particle, it's been deflected towards the positive plate. Well, why is that? The beta particle has been attracted towards the positive plate, of course, because it's an electron with a single negative charge, and opposites attract, so the negatively charged electron is attracted towards the positive plate. So next, let's think about our alpha particle, and again, it's a case of opposites attract in this case. Okay, the positively charged alpha particle has been attracted towards our negative plate down there. Okay, but this time the amount of deflection is different again. We see the beta particle being deflected there. We see the alpha particle not being deflected as greatly there. Well, why is that? Well, because our alpha particle's got 2 protons, it's got 2 positive charges, one from each of the 2 protons. So the force of attraction between our charged particle and our charged plate is twice as great. But here's the thing, the mass is so much greater of the alpha particle than the beta particle that the deflection is still less. So even though there's more attraction between our alpha particle and our negative plate, because this has got 2 positive charges compared to the 1 negative charge of the beta particle, the fact this alpha particle is 8,000 times more massive means the deflection is not as great. Okay, and finally, what's the last thing we need to think about? Well, of course, it's our gamma ray there. Finally, the gamma, we can see that there's been no deflection. It's because the gamma radiation is simply electromagnetic radiation, and it has no charge at all, so it's not affected by this electric field. In the exam, what they may do is give you one of these diagrams, or they might give you both of the diagrams, and ask you to predict which way the alpha, the beta and the gamma will be deflected by a magnetic or electric field. Okay, so you need to know what happens to them and why.
So that's what you're going to need to know about the nature of alpha, beta and gamma radiation. And remember, you are going to need to understand and be able to explain the diagrams of the magnetic and electric field that we looked at. Any problems at all, don't hesitate to tweet me at Mr_Pepperell or email me and I'll get back to you ASAP. Thanks for stopping by.